All right, so tonight we're going to talk about recommendation systems, which are basically what services like Netflix and Spotify use to kind of recommend different movies or songs to you based off of what other users like, similar users, and then also similar artists or similar movies. So you can do this a lot of ways. Kind of a simple way is just to recommend people the most popular items, the most popular movies or songs. A better way that's used a lot more often is called collaborative filtering. So that's what we're going to kind of focus on here. And there's basically two different ways you can do it. You can either focus on the users and find similarities between them, or you can focus on the items themselves and find similarities between those. So looking at these pictures, in both we're concerned with this guy here. So we'll look at the user-based one first. So for the user-based one, we basically want to find another user who's similar to this guy, and then look at what items they like and suggest ones to him based off of the ones they like that he doesn't already like. So it looks like he likes the strawberry and the watermelon. And then we'll look and find someone else who likes strawberry and watermelon. So this person only likes the strawberry. This person likes both the strawberry and the watermelon. So then we look at their other likes, so the grapes and the orange, and then those end up getting recommended to our person of focus here. So that's kind of user-based in a nutshell. On the other end is item-based. So in this case, we want to compare the items. And so if someone likes one item, we want to suggest an item to them that's similar. So in this case, we're still focusing on this guy at the bottom. And in this scenario, he just likes the watermelon. So we want to find something similar to watermelon. So it seems like, at least for this girl, she likes the watermelon and the grapes. So that means the watermelon and the grapes are kind of similar. And then also the person at the top likes watermelon and grapes. So the number one suggestion then would be grapes to him. We could also probably suggest the orange because the person at the top also likes orange as well. But since both of these two like the grapes as well, that's a bit stronger of a similarity. So in this case, we'd recommend the grapes. So that's kind of user-based versus item-based. Both have their merits. Usually if you have a really large database, you want to go with the item base. It can be better in terms of memory. And also, usually your items are pretty constant, but users can change. So, users can change their taste. You can get influx of like new users who are different at any point, but your items generally stay the same. So if you can establish that some are similar, that can usually be a stronger way to suggest new items to people. All right, so you can do this just using basically a data set and kind of just finding similarities between users or items, or you can train a model to learn those similarities, and then you can plug in new information basically and make new suggestions. So that's kind of what's meant by model-based versus memory-based is the other way. So for model-based, we have a lot of different options. Some of these you might not recognize and we might not actually go into, but for example, KNN is in here. So K nearest neighbors, it's a clustering algorithm. So you can basically, find groups of items that are close together in some space or in some dimension. And say that those are likely similar and recommend those. There's also SVD, which we'll talk about a little bit. It's singular value decomposition. It's basically a dimensionality reduction tool that's really similar to PCA. So those are some options. And then the Python packages you'll use for these are mostly surprise, which is from scikit-learn. There are some ways to do this without, and just kind of with like native Python and NumPy, but surprise is the best library for it. So that's what we'll be using. And then you can also actually take this to deep learning, which we'll cover here in the next mod. So, neural networks that can also learn the similarities between items or users. All right, so to determine if items or users are similar, we need some metric for that. And there are quite a few. I'll just go over two of them here that are used the most. The first is cosine similarity. Here's an example. This is basically how you would calculate it. It's basically based off of the angle between two vectors of, these could be two items or two users. So basically, the closer they are together, the smaller that angle is going to be. And so the more similar we would say they are. Whereas if it's like a really wide angle, then they likely aren't similar. So that's probably the most popular one you'll see. Another is called Jacquard similarity. It's calculated a little bit differently. So in this scenario, say we have these two sets. So you could think of this as like user 1, and these are the things they like, and then user 2, and these are the things they like. And we're trying to compare and determine the similarity between the two users. So in this case, you find the union of all the things they like. So basically take everything from both of the two and put that in this union object here. And then you also take the intersection, so the things that they like in common. And you basically divide the union by the intersection, and that ends up giving you the similarity. So if they have a lot in common, you'll get a really high score here. Whereas if they both like a lot of different things and they only have a couple in common, then you're going to get a lower similarity score. So that's kind of two of the metrics you can use. There's also the Pearson similarity as well. And there's some more, but those aren't used as often. So these are kind of the main ones for now. So to start off, we're going to do a user-based example. So this is a data set that is on sushi rolls and basically people's, whether or not they like them. So there's different kinds, California roll, salmon roll, all those. The rows correspond to different users or customers. And basically if there's a 1, that means they like that particular roll. In this case, you can see it's filled with missing values, which we'll have to fill in here in a second. But that's basically because we don't know that this user likes, salmon or tuna. We just know that it likes the California, tempura, tiger, crab, spicy tuna. So that's kind of our data set. And this is a small example. You usually have a really large database of users and items, but this is just starting small. So to start off, we have to fill the data frame, get rid of those missing values. So we'll just put a 0 in for everything, and then keep the ones as they were. So we'll go ahead and run that. All right, so we're going to import this cosine similarity function. This basically takes in two vectors and calculates the cosine similarity between them. So we'll import that. And then on this next cell, I'm going to compare customers 1 and 0. So I'm going to basically take this row as one vector, this row as the second, and find the cosine similarity, or kind of the angle between them. And we'll see how similar they are. So we go ahead and run that, and you get about a 0.51. This is between 0 and 1, so the closer to 1, the higher the similarity. So they're like moderately similar, not super similar though. But then we can do customers 1 and 2 and see that they are a lot more similar at 0.81. And if we go back to our table, we can kind of see why. So customers, let's see, what did I plug in? 0 and 1. So they have California in common and tempura, but that's about it. Whereas 1 and 2 have both California, salmon, and it looks like just those, but then neither of them have tried most of these others, and none of them like most of the others. So they actually end up being more similar. All right, so with that, now we can make recommendations for our customer. So we're going to pick customer 4, and we're basically going to run down through and calculate the cosine similarity between customer 4 and all the other customers. And then this all just kind of stores it in a data frame, sorts it at the end so that we can see which customers are most similar. So in this case, we can see that, of course, customer 4 being the one we selected, it's going to have a high cosine similarity with itself, but actually customer 2 has 1 for the cosine similarity. So if we go back to the table, 4 is here, and then 2, we can see that they actually are identical. So in that case, we can't really gain anything from customer 2 to suggest to customer 4. So we would want to look at the next one. So it looks like customer 1 has still a high cosine similarity at 0.82. So let's go ahead and look at 4 and 1 then. So here's our customer we're trying to recommend, and this is the one that's most similar to it. So can anybody kind of look at this table and tell me what kind of role you think we should recommend to customer 4?
Tempura.
Yep. And why is that?
That's the only difference. That's the one customer 1 likes and customer 4 hasn't tried yet.
Yep. So in this case, it's pretty easy to tell. They both like Californian salmon, but then customer 1 likes tempura. So in this case, we would suggest that to customer 4.
Is that, Matt, is that kind of a drawback with this, that because this customer's only tried 2, they're going to be most similar to someone else who's tried very little? So there could be another customer that also likes crab roll that could also be a good match, but because this customer hasn't tried any, they'll show up as less similar.
Yeah, that's true. And that's also just kind of because this is a small data set and it's kind of made up. But yeah, I mean, ideally you want basically, in this case, this is 0 or 1 for the values. So it's basically saying whether or not they like it. But ideally you'd want them to actually rate it and give it kind of a score. And that's actually called implicit versus explicit ratings. So explicit would be like if you ask them to score something out of 5, give it like 3 out of 5, 4 out of 5. Implicit is just, you're not actually asking them directly, it's just based off of their behavior. So this would be implicit, which is basically they've ordered this kind of roll before. So we don't actually know that they like it, we're just kind of assuming it's implied. But in the next example, we'll look at more of the explicit. But yeah, in general, user-based is used a lot less. It does have downsides to it. So that's good to point out.
Thanks.
All right, so we're gonna use another metric now, the Jacquard similarity. For this one, we have to make a function, but you basically create the 2 sets. So if you think back to that picture, like the 2 arrays with the characters, and then you're going to take the intersection of the 2 and divide it by the union. And so that will give us that similarity. We'll basically do the same thing again. In this case, though, since we're dealing with sets, we have to have basically lists of the different types of sushi that they like. So in this case, these are each of our customers. We're just creating a list of the sushi that they like. And then these will be the arrays that we pass in to the similarity here. So in this example, we take the second customer and the first and compare them and see that they're somewhat similar. And then this got cut off, but we make a data table again, a data frame again, to kind of compare all of the other customers to customer 4. So in this case, it looks like we would also recommend customer 1's suggestion, so tempura. But in other cases, you might see more or less similar results using the 2 different metrics. Sometimes they can vary a lot, other times they're pretty close, kind of just depends. But yeah, so that's another metric, that's another way to do it. Now we'll take a look at an item-based example, and for this one we'll actually use surprise the library for. So we're going to use a similar data set, except if I can get this to work. There we go. Okay, so this time we have actual values or ratings. So in this case, this is explicit rating because we asked all these customers to rate the sushi that they've tried on a scale of, I think it's 1 to 5 here. So there's the recommendations. So to use surprise, you have to pass in a data frame with a certain structure. And the structure is basically a column for users, a column for the items, and then the ratings that they gave them. So this code here basically does that. It takes our data frame from the format back here to something kind of more stacked, or I guess long format here, as you can see. So we have each of the customers for each sushi and their rating. All right, so to use surprise, you have to import a couple things. You basically need an algorithm to use for it. So in this case, we're going to just use the k-nearest neighbors basic one. And then you also need this reader object and data set. The space is not working. Okay. And so this is kind of how you load a data set into surprise. So you create a reader, pass in rating scale. So whatever the ratings are based on, in this case, it's 1 to 5. Then you create your data, which you can load from a data frame. And in this case, you need to fill it with 0. So since our scale is from 1 to 5, if we fill it with 0, that's outside of that, so it won't mess it up. If our scale was like 0 to 5, then that would basically tell it that everybody scored it badly. But in this case, it's outside of that, so it just basically allows us to pass it in and allow it to load the data frame. And then you can create a dictionary of options here. So you can choose your metric. In this case, we're going to use cosine similarity. And then you also can choose whether or not it's user-based. So if this is true, then it would be user-based like our first example. If it's false, then it's going to be item-based. And you'll get different results depending on what you choose. And then you create your algorithm object, so the KNN basic, and you pass in your option parameters here. And then you have to fit the algorithm similar to sklearn. But what you pass in, you actually have to call this .build full train set off of your data object. This is kind of just the way they make you do it. It's kind of lengthy on what you have to do. It's not like sklearn where you can just kind of pass it directly in. You have to kind of read it into this particular format and then do this .build full train set. So that's what you do. You run this, and I have to rerun the one cell that had this one. And it'll say computing the cosine similarity matrix, and then when it's finished, if you have a really big data set, this will take a lot longer, but since ours is small, it's really quick. And just to remember what our data frame looks like, which it should be this other one, what did I call it? There you go. All right, so now we're going to, again, get predicted ratings for customer 4. So we have our customer here. We're going to look at all the ones that they did not rate already, and we're going to try and predict how they would rate those other kinds of sushi. So for each of the sushi that we did not already rate, this customer 4, we're going to call predict off of our model. And when you predict, you have to pass in, this should actually be customer. So you pass in your user and then your item is kind of the format. So we'll rerun that, and they are all ones. So I think something got messed up loading the data frame. Let's go back. So we got that, and then this is called DF as well. Yeah. Okay, those are all there. That is weird. I might have to troubleshoot this while you guys do the activity, but if you could see before I ran it, we did actually get different values. What it should print out is basically predicted values for the ratings. So it should be, you know, somewhere between 1 and 5 on whatever it thinks the customer that you're passing in would rate those particular sushi. So chat. Yeah, so Jacob has it. Did anyone else run this and get not all ones?
Yeah, I did.
I got all ones.
But Anubhav, you didn't get all ones, or you did?
No, I did.
Few.
Okay.
But when I passed 0, it was different.
I'm sorry. Yeah, when I passed in 0, I got different values.
Oh yeah. So in that case, it's 4. Okay, maybe they are all ones then for customer 4. Let's try another one.
Yeah, when I pass in 4, I get all ones.
What is the first item in predict?
So it should be the user ID. So like our index in this case. Yeah, it should be UID, and then this other one is IID. Must be how it was set up here, data TF. That looks fine there. Yeah, 1 to 5. Yeah, because it's only different if it's 0.
No, 14,
And
13. I think for certain numbers, they are the same. Like
Okay.
they are in difference with these choices.
Okay, so that just might be a result of like how small the data set is,
Yeah.
and of how sparse it is. So like a lot of the customers have only rated a couple of the sushi. So maybe at the end we'll try adding some values in to fill it in and see if we get different numbers. But generally you shouldn't get all the same. That just might be a result of the smallness of this data set. But in the activity, you're going to use a large data set, so you should get different results then. All right, let's keep going. So as I said, you have to pick a prediction algorithm. So we chose KNN basic. It's kind of just a simple one to use, but these are the other ones you can use. So there's a KNN with means, which takes into account the mean ratings of each user, as it says here. And there's kind of just different ones you can try out. There's SVD, which I'll talk about here in a second. This one can be pretty effective. It's basically what was used by this guy, Simon Funk, when Netflix was doing a big contest to basically set up a recommendation system for their movies. So that can be an option too. But yeah, you can kind of switch them out. You can also do, I think the curriculum mentions that you can do kind of a grid search and actually build different models and change the parameters, changing out the algorithm, and kind of see the different results you get. But yeah, there's that. So then SVD is singular value decomposition. The math for it is complicated. We're not going to go into that tonight, but I do have a video or two you could watch if you really want to figure out how and why it works. But what you need to know is that it's similar to PCA. It basically reduces a matrix with a lot of features, a lot of rows and columns, down to a much smaller one. To basically, you can choose like PCA, how many components, and it basically does that and tries to still capture, you know, the relative information. And this is kind of the formula for it. So on the left would be like our table of values, like our ratings and our users. And then this middle part here is actually the singular values. And then there's a left and a right array basically. And so this formula means that any array can be broken down in this manner. And you can end up with your singular values, however many you choose to have. So we're going to use that right now to give you an idea of how it works. So you want to import it from sklearn, and you want truncated SVD so that we can specify the number of components. So here I'm just going to pick 2, and I'm going to fit and transform my data frame. And I have to fill the missing values like usual, and then I'm going to transpose it because I want to look at the items first. So this is basically going to flip the users and the items, the rows and columns. So we'll run that and then take a look. So we end up with 2 features, just like PCA, 2 components. Now, since we have that, we can actually just plot it and label the different roles here. So now we have the roles in 2D space kind of spaced out. Some are grouped together. So from this, you can see that we could run some kind of unsupervised machine learning algorithm on it, some kind of clustering method in order to basically group these. And then, roles in the same group would kind of be recommended to the same customers. So you can imagine like this would be a group, maybe this one, and then these would kind of all be separate ones. So that's always an option. If you have, a ton of users, a ton of different items, SVD can kind of shrink that down because it is really computationally expensive to run the surprise algorithms on like a giant data set. The one I give you for the activity is actually originally much, much larger, but I had to cut it down because it needed something like 30 gigabytes of memory just to run and build the model. So then to flip it around, this time I'm going to run the same thing, but just the data frame as it is. So in this case, we'll get actually the users and see how they're kind of grouped. So you can kind of see the labels here for the different users or customers. And again, we could, do some kind of clustering on this and basically come up with different groups that are similar. So that's another option as well. And then this is kind of some intuition behind how it works. So this would be like doing SVD into 2 factors, factor 1 and then factor 2. And if we did this for like a movie database, maybe those factors correspond to something like whether or not it's more serious or more funny, and then different movies would fall along that axis. And then on the X here, the factor 1 to the negative could be geared towards females, and to the right could be geared towards males. You don't actually know what those features represent. This is just kind of a way to think about it. It basically gathers some kind of latent information about the movies and kind of spaces them out that way. So whenever you do SVD, you don't actually get, oh, these movies are more serious or more funny. That's kind of a downside to it. It's not really interpretable. You don't know what those components actually mean. Just that they capture something about the information that you give to it. So this is just kind of a way to think about it more intuitively. All right, so before we go into the activity, which is going to use basically all this stuff that we just talked about, does anyone have any questions?
Hey, Matt. So I run the item-based and user-based code, and I got very similar result and different with your grouping.
I was gonna say the same thing. I got a different graph when I ran that.
Let me see here.
You guys have different values though?
Oh yeah, I have different values for DF transform.
It is a random state. Let's just try making it 4. I don't know if that'll actually change anything.
I mean, isn't the matrix going to be different because it's randomly chosen?
You mean this? Or
This table looks the same.
okay, so does everyone have this table here?
No.
Wait.
I have different values, but I have the same table.
I have different values. Did you change anything to the?
I really think it's because the ratings that we made was randomly chosen between 1 and 5, weren't they? Like the options.
Let me see here.
But then your matrix will be different, so our values will be different.
Well, okay, so check your check this part here. Do you have the same table?
No.
Oh, wait, do you guys have code that's not here, like above? Oh. Okay, so I didn't update it after I took that out. That was basically how I generated it. So that kind of randomized it. So you will get different answers then if you run that. But if you just read in this Sushi Rex 2, then you should get the same as me.
And again, how can we interpret the chart? Is it basically just treat them as points, and like if they're closer to each other, they are one cluster?
Oh, you mean down here?
Mm-hmm.
Yeah, so this is, only using 2 components, but basically the ones that are closer together are more similar. So if you did, a clustering algorithm on this, it would kind of group them in some way. And it's kind of like this picture too, this one.
So we'll make prediction, let's say, like if you go back to your chart, what if this person likes salmon and California, what will be the next we recommend them? With the Philly or tempura?
So in that case, you'd probably find the closest to each one. So salmon is maybe tempura and Philly is maybe California. Or you could probably find like the middle point between the two and then find the closest to that. And in that case, it would be Philly.
Okay.
Is this like PCA where the x-axis is more important than the y-axis, or is it?
I believe so. It works that way too.
So how this get us a prediction in the code?
So to take this to like a prediction then?
Yeah, like SVD.
Well, so you can use SVD in the surprise as one of the algorithms here. If you actually wanted to use it, you'd probably want to go that route. This is kind of more like from scratch. So you would want to run like your clustering, and then I don't know, that way you'd have to double check on the whole, if you have 2 that you like, finding one that, is closest to both of them. This would be more so if you were just given one item as an input, like, oh, I like salmon, so I should try California because that's the next closest. Or I like Philly, so I should try spicy tuna crab and tempura.
Okay.
Does that kind of answer your question?
Yeah, I guess.
In this activity, you can probably use the SVD, to kind of try that out. But yeah, I mean, usually you would just use this. This is just kind of a way to like explain how it works. You wouldn't necessarily like use it this way. It's just kind of to get like a visual.
Cool.
All right, so let's go into the activity then. All right, so this is from an anime database. It's basically ratings on different anime shows. I condensed it down to like the top 1,000 users, or it might be 1,500. I might have changed it. And then only the top 100 shows. So it's smaller, it's easier to fit into your memory and to run your model on it. So you're going to follow these steps. You're going to do a train test split. They outline how to do that here in the surprise documentation. They also do this in the curriculum in one of the labs in the READMEs. It's similar to sklearn, but a little bit different. And then I already have the import here. So you do the train test split. Then you're going to choose a filtering method. So choose either item or user base, and then also choose one of these algorithms. And you'll kind of build the model like we did above. Then you can check the root mean squared error of the model by seeing the predictions on the test set and then what they actually were. So that way you have some metric to determine the performance of your model. And then after that, you'll kind of tweak your model or try out a slightly different one, maybe switch to a different algorithm and compare the performance on those. And then once you have like your final predictive model, you'll want to do this last part where you recommend the top 5 shows for user number 47 or index 47. So that's kind of the game plan. And we have 1, 2, 3, 5 people. So we'll do a group of 3 and a group of 2.
Can you guys see my screen?
Yep.
Cool. So first of all, just read both data sets and check the unique ratings. And it seems we have a negative one. So actually that's like the lowest rating, and we only want to keep the positive ones. So we import the libraries. I chose to use SVD this time. And we do the train and test split. This is a tricky part. We took some time to get this to work. Seems like you have to use this rater to process your data set first and then do the train test split. So here we first read this data, get rid of the NAs, and then do the train and test split with a test size of 0.15 and random state 4. And algo is SVD. And I chose n factors equals 3 first, and random state equals 4. And then fit the train set and make predictions on the test set. And next step is to check the root mean square error, which is the import RMSE from surprise accuracy. And we're able to get a RMSE of 2.16, which means that our prediction will be off by 2 points out of 10. So that's pretty good. And I also tried Kagan basic. So use cosine, similarity, and item-based filter. And I first chose a k equals 5, a minimum k equals 2. And I got a slightly higher RMSE. So the next step I did was to just iterate and find the best k. So first I iterate 1 through 9, and it seems like the larger the k, the lower the RMSE. So then I continue to iterate through 10 through 19, and found an optimum point around 14, I believe. So this seems to be our best MSE from KN Basic, and it's still higher than SVD. So it looks like SVD result is slightly better. Then we use SVD for the next prediction. What are the top 5 shows? So that's where I'm at now. First of all, we try to find the shows that user 47 already watched. And then we need to filter the whole list and get the non-watched, like shows that never been watched. You guys know how to filter a list? Should I just do a filter? Anyone want to chime in?
I don't know.
Yes.
I feel like you have to go through every single one and like move the values so that it's in ascending order.
Really?
For a list, I think so, right?
Or
So
maybe we can exclude those after we get the result. Does it work?
you could do it before or after. I think it's easier if you do it before. So what you could do, actually, if you bring that cell back, so you have your list of ones you already watched.
Yes.
So what you can do then, I think there's a not is in. Let's see, pandas not is in.
I think I use lambda.
You probably could. I think there's let's see, not logical not. Well, that's maybe a bit. Okay, so what you can do is, so you have your ratings.
Mm-hmm.
So go ahead and call the like ratings data frame. And then we want where ratings, so like the filtering, where, yeah, anime ID. You actually want this thing, put it in chat. So that thing, and then replace the column with anime ID, and then the value with your list of watched. So it'll basically get all the anime IDs that are not in that list. And then switch out value with watched list.
Let's see.
And then on the outside, do rating and then brackets.
Mm-hmm. Rating?
Like on the very outside, so on the left-hand side.
This?
No, like in front of the NP. Like you want the rating data frame where this condition.
Oh, okay, I get it. So like this.
Or you only need the first one.
Hmm?
Yep, like that, and then a bracket, and then a bracket at the end. And then one more set of brackets at the end and call the column you want. So the anime ID, and then dot unique.
I think this is already done unique. Cool. This is like the
Try that. See if that works.
worked. Let's print this. Oh, nice. So So this part basically I construct a data frame and store the movie name and ratings in a data frame and then sort it. Looks like the top 5 films are here. Cowboy. Nice.
Cool.
Thanks for your help.
That looks good. Does everybody understand how we did that, creating the list of movies they haven't seen or shows? So like the is in part checks if the items are in that list, and then wrapping it in that np.logical not just means the opposite. So the ones that are not in that list. It's the same as like if you're doing like an equals and you want to make it not equals, you put like the exclamation mark, it like negates it.
Yeah, NumPy makes this very easy.
Yeah, I mean there should be a way in pandas, like because you have the is in, they should just have like is not in or something, but this is built around it.
Cool.
Yep. Well, thanks, Bonnie, for going over that.
You're welcome.
Anyone have any questions on this before we go? I'll take the silence as a no. Did you guys like this topic? Do you like working with recommendation systems, or is it kind of eh?
It's whatever.
It's really interesting. Yeah.
Yeah, I think
found it very interesting.
it's a cool topic. It's a little tricky to get my head around it at the moment.
Yeah, and it's kind of hard to cover in one study group. There's a lot to go into, but this at least gives you like an overview of it. And you probably won't use it in your project here coming up, but you're at least familiar with it, and you could do something similar if you had to.
I was considering about ensemble methods. How do we use ensemble methods in different contexts? Can we like do different algorithms at the same time?
What was that first part, sorry?
So I'm not sure if I fully understand ensemble methods, but to me, it seems like you use different algorithms and to perform on one task, right? And to find the best algorithm. So I've been thinking to solve different problems like recommendation, can we use the same thing? Like towards the same line of ensemble methods?
Yeah, you probably could. You could, train a couple of them using the different algorithms or whatever, and then either do it like kind of like a voting classifier. So like, tallying up whatever items are suggested or whatever. Yeah, you could definitely do some kind of ensembling with it. There's not like a built-in way though, so it'd have to be kind of by hand.
Okay.
That could probably work, yeah.
Yeah, again, I feel like this module would be a like full 4 months course in a grad school. So we really covered a lot.
Yeah, no, honestly, this module should be about twice as long as the other ones.
Yeah.
We really wanted to go into that, but we'll be like revisiting some of it next mod too. So it'll kind of continue over a little bit. And yeah, and actually I've decided that next Monday we're going to start the project. So we're going to go through a bit of content, and then at the very end, I'll just like show you the project. Because like I said, you do have to find your own data set for this one. So I want to get you guys a jump start on that. And like I said, it's for a classification task. So you can kind of start looking now, some kind of data set, or somehow you can, web scrape some site or an API to build a classifier. So keep that in mind. All right, well, thanks for coming, everyone. Have a good night.
Thank you. Bye.
Bye.